All right. Last thing we've got to do for the circulatory system, and then I can give you a fun and exciting exam probably next week. We need to finish blood. Now, blood's role in oxygen transport, CO2 transport, we will cover that with the respiratory system. So I just need to go over just some physical characteristics of the blood real quick, and then we can wrap up circulatory. Now, what you're seeing here, imagine this is a test tube. All right, you put a sample of blood in it, and you let it separate. Blood is a connective tissue, like those other connective tissues you might have looked at last semester. That is, it's got a cell component, but it's got the majority of a non-cellular matrix. So now what we do with this tube, what it's showing you, you separate it. The cells are a little denser, so they will sink to the bottom. Typically, you'd spin this in a centrifuge to speed up the separation. But the cell components are down here, they're denser. This kind of straw-colored light yellow material up here, that's the matrix. It happens to be a fluid in blood. It's called plasma. So this is all a plasma. About 55% of the blood's volume is, 55% of the blood's volume is plasma. So it's the majority of the blood. The remaining 45% or so, it will vary from person to person, depends on your health, your sex, and so forth. But 40, 38, 45, somewhere in there. That is what they call formed elements. These are cell components. Now, we've looked at the cell components before in lab. Of this 45% that's made up of cells, over 99% of it is red blood cells, the erythrocytes. Their role primarily is transporting oxygen, CO2, and buffering the blood a little bit. They absorb hydrogen ions. So that's most of this component here is the red blood cells. You see this little white line right here? They call it a buffy coat. That is the white blood cells and platelets. They are less than 1% of the cells. And of course, we looked at them in a PowerPoint. The white blood cells they play a role in infection fighting, immunity, that sort of thing. There's also platelets in here. Platelets play a role in hemostasis or blood clotting. Now, this sample is showing here, this is called hematocrit. If you take a blood sample, spin it down, separate the cell components, what they call the formed elements, this percentage, which is, let's say, 45%, that's also your hematocrit. The reason this is critical, a couple of reasons. Most of this hematocrit is red blood cells, which are small cells, little biconcave discs, that contain hemoglobin. Hemoglobin is essential for increasing the blood's oxygen-carrying capacity. Blood with hemoglobin in the red blood cells, that is normal whole blood, can hold about 20 milliliters of oxygen in 100 milliliters of whole blood with the hemoglobin and the red blood cells. The plasma alone can only hold about 0.3 milliliters of oxygen per 100 milliliters of plasma. Not nearly enough oxygen to supply our needs. Now, the other thing we'll mention with the hematocrit, it also affects the viscosity of the blood. Viscosity is it's a fluid's resistance to shear forces. Basically, it's how thick it is. Water, if you say it has a viscosity of about 1, typical blood is about 3 times as viscous. It's thicker, more syrupy. It's got a viscosity of about 3. Yes, blood is thicker than water, literally. That viscosity plays a role. It affects the blood's resistance. Remember, when you're looking at flow in the circulatory system, flow is determined by blood pressure divided by resistance. Resistance, again, a lot of things affect resistance, blood vessel diameter, blood vessel length, and so on. But one of the things is viscosity. If this hematocrit gets too high, yes, the blood can transport more oxygen per milliliter, but it gets so viscous, it's like trying to push syrup through the blood vessels, and eventually you can't move it. It becomes too viscous, too much resistance. So what we'll do in a moment, I'll go ahead and we'll talk about the effects of viscosity a little bit here up on the board in a moment. I may put up a couple of slides of white blood cells as well. So hold on a minute. Alrighty, let's see. We're going to wrap up circulatory today. This should be the last batch, unless I forget something I'll put up later. So that means quiz coming up. I put it up today, this afternoon. It's Monday. And then next week, exam. The exam, number 2 for lecture, is going to cover genetics, which we already did. We covered that in lecture. Somebody had a quiz on it. Basically, terminology, those Punnett square little crosses you did. So that should be a piece of cake. And then the circulatory system. Not sure exactly the format of the test, but you can figure, 50 to 75 more or less multiple choice questions. Kind of like you've been running that last quiz I gave you. You'll do it on Connect, and you'll have Basically, if it's a 60-point exam, I give you about 60, 65 minutes to do it. No going back. Kind of the same way the quizzes are set up. All right, now the blood real quick. Again, we're not doing much with the blood because we'll cover a little bit more when we get to the respiratory system. I just kind of want to get through circulatory so I get you an exam, get some more grades up there. But as you'll see in the next little video with prettier pictures, if you take a blood sample, take a bit of blood out, put it in a test tube. Blood is a connective tissue. It's got a lot of non-cellular matrix with cells suspended in it. It happens to be a fluid. The matrix is fluid, so it flows. But if you take a blood sample, and typically you put it in a test tube or a capillary tube, and you spin it, the centrifugal force will separate the components of blood based on their density. And what you'll find is about 45% of blood volume is going to be cells. Again, that varies person to person. It's a little higher in males than females. It might be 38% cells in a female, 44 or 5 in a male. But that's the cell component. The rest of this, the remaining 55%, is the matrix, which we call plasma. I'm not going to talk a whole lot about plasma. It is important. Most of your nutrients are carried in plasma. Hormones carried in plasma. All the ions are carried in plasma. Globulins, antibodies are in the plasma. Transport proteins for the hormones in the plasma. So there's a number of plasma proteins like albumin, fibrinogen, which plays a role in blood clotting. So there's a lot of stuff in the plasma. It is used to transport, again, nutrients, waste material are in the plasma for the most part. The cell component consists of primarily red blood cells. So of this 45%, 99% of it are RBCs, red blood cells or erythrocytes. They make up 99% of that blood volume. Now, what do erythrocytes do? What do red blood cells do? They're basically little membrane-bound bags of hemoglobin. There's a little bit more in there, but all of the formed elements, all the cell components of blood, they're made in the bone marrow. But when the red blood cells are released into the circulation, most of the organelles are ejected. They have no nucleus, they have no mitochondria. They're really stripped down cells. Like I said, they're basically little bags that contain hemoglobin. We'll look at its structure a little bit later when we look at the circulatory or the respiratory system. But hemoglobin is an oxygen binding molecule. It's a protein with a metal atom on it and iron. Each hemoglobin can actually chemically bond with 4 oxygen molecules. Now, the reason these things are so stripped down, at least in part, the red blood cells are carrying oxygen. You don't want them to have aerobic metabolism. Then they'd be burning up the oxygen that they're carrying. Kind of like, when I get fired from this job, I get a job down driving a beer delivery truck to all the little quickie marts. But there's a door between the cab and the back of the truck. Well, if that's the case, I'm going to be driving to the first gas station, reach back, get a few, go to the next gas, by the time we get to my last stop, there's nothing left in there to deliver. So you basically don't want to burn up what this cell is specialized to transport. That's why no mitochondria. It's very, very reduced metabolism. So basically little bags of hemoglobin. And they're small cells. If you measure them sort of on the long axis here, they're about 8 micrometers. Now, the reason we have hemoglobin, if I took blood without the hemoglobin in red blood cells, let's say I took a test tube of just plasma. There, this will be 100 milliliters of plasma. Now, I let this plasma reach equilibrium with the surrounding air. Let's just say it's air that's in the lungs, which has a concentration of oxygen that's referred to as a partial pressure of oxygen. We'll talk about that later. 100 millimeters of mercury. But basically, the amount of concentration is the same as you have in your lungs. Now, the oxygen will diffuse into the plasma. It will diffuse in until you reach equilibrium, equal concentrations. Then if I took that plasma and I pulled it out and I analyzed it and I checked how much oxygen is in it, I would have something like 0.3 milliliters of O2 per 100 milliliters of plasma. It's basically the same amount of oxygen you find in a freshwater creek. There's oxygen in there. That's what the fish can live. There'll be a little in there. But contrast that with whole blood, with your 45% cells, which are mostly red blood cells with hemoglobin. If you do the same thing, take whole blood, allow it to reach equilibrium with air that's basically the same composition you'd have in the lungs, pull that 100 milliliters of whole blood out, analyze it for oxygen, what you find is there's about 20 milliliters of O2 per 100 milliliters of whole blood. That's what is it? That's almost 70 times as much oxygen. That's why hemoglobin is important. If our blood were just plasma, there's no way we get enough oxygen to tissues. Not without increasing, blood flow, cardiac output like 70-fold, and heart this big would work. So hemoglobin, its main function is to increase blood's oxygen carrying capacity. It can hold 60, 70 times more oxygen than the same volume of plasma. That's why it's there. So that's the benefit. Now, this volume of red blood cells, you may see that, if you ever go to the clinic, they take a blood sample, they'll measure this component. It's usually referred to as hematocrit. Hematocrit. Okay. Hematocrit is the volume of blood cells in a particular volume of whole blood. That 45%, again, it's almost all red blood cells. So if your hematocrit is 45%, what it means is 45% of your blood volume is made up of red blood cells. That's an indication of how well your blood's going to be transporting oxygen. Now, it has one other side effect. These red blood cells also contribute a lot to the blood's viscosity. That is how thick it is. Remember, take a straw and try to suck water through the straw. It's pretty easy, right? Take that same straw, stick it in a cup of Karo syrup, and try and suck it through the straw. Doesn't move as well, right? It's much more viscous. It's thicker. That's what viscosity is. So while this hematocrit is important for your blood's oxygen carrying capacity, you might think, well, if I increase hematocrit, that's even better. I can get even more oxygen in my tissues. I can run, win marathons, which is true to a degree. Athletes typically have a slightly higher hematocrit. It aids oxygen delivery to tissue. But if you increase it too much, there's a point of diminishing returns. If the hematocrit gets too high, yes, your blood will carry a lot more oxygen per unit of volume, but it starts to become like pushing Karo syrup through your blood vessels. It doesn't move. So hematocrit, while it does increase oxygen's carrying capacity, it will also affect the viscosity of the blood. It's one of the main components to affect viscosity, or how thick the blood is. If the blood gets too viscous, too thick, it gets hard to push through the tubes. Some people will get an abnormally elevated hematocrit because, congenital heart defects or something along those lines. They call it polycythemia. Same thing will happen to some people when they go to high altitude. Their hematocrit gets too high, they get polycythemia. Now, what controls production of these red blood cells? As I mentioned, all the cell components, what they sometimes call formed elements, they're formed in the red bone marrow. You need to keep a certain amount of hemoglobin and red blood cells in the blood to ensure adequate oxygen delivery. Well, it turns out the organ that's kind of monitoring this is your kidneys. The kidneys can monitor the oxygen content of the blood that is being delivered to the kidneys. If it gets too low, the kidneys have a hormone they'll release. See if I got a little bit more room up here somewhere. I'll try it up at the top here. It's called renal erythropoietin. That is a hormone. We didn't discuss it with the endocrine system because, again, it's just dispersed cells in the kidneys. But renal erythropoietin will be released by the kidney if the blood going to the kidney is hypoxic, low in oxygen. If the blood going to the kidney is low in oxygen, kidneys will release renal erythropoietin. And guess what it targets? Yes, the red bone marrow, and it will increase red blood cell production, trying to increase hematocrit, your blood's oxygen carrying capacity. That's partly why athletes have a higher hematocrit. When you're vigorously, aerobically exercising all the time, your blood gets a little low in oxygen, a little hypoxic. That stimulates the kidneys to release renal erythropoietin. We slow that down, renal erythropoietin, which will up your hematocrit. So that's the hormone that affects red blood cell production. And it's controlled by the kidney. Now, it is a slow hormone. There's about a 10-day lag. So if you're a little low in oxygen, you won't see an increase in red blood cell production for, 10, 12 days or so. This is also one of the things we use when we go to high altitude. If you go to Vail skiing or Leadville, Colorado, to mine lead, those are pretty high towns. When you first get there, there's not enough oxygen in the atmospheric air. You get a little fatigue, you're winded easily. It takes about 10 days to adjust to that lower oxygen level. One of the adjustments you'll make, you'll release renal erythropoietin, your hematocrit will go up. That will allow you to tolerate the lower oxygen levels. Now, part of the reason I mentioned this can affect blood pressure and blood flow as well. Do you remember early on, I think we were still in the classroom, but when we want to determine the flow of blood through a tube in the circulatory system, that's basically cardiac output, it's determined by blood pressure over resistance. So, get over here so I don't cast as many shadows. So flow in the circulatory system or through a blood vessel is determined by blood pressure, that's the force generated by the heart, divided by resistance. If you increase the pressure, all else being equal, you'll increase flow through that tube. Resistance has the opposite effect. If you increase resistance, if this number gets bigger, that'll reduce the flow if the pressure remains constant. So one of the components of resistance we looked at was blood vessel diameter. That's a big one. That's exponential effect for power. But this is also where hematocrit comes in. If the blood gets too viscous, it won't flow as well through the blood vessels. That means oxygen delivery, blood delivery will be reduced. So that's resistance. That's a bit of hematocrit. I'll splice a couple slides onto this. Take care. All right, so this is a blood smear right here, and it's just showing you some of the components. Now, all of this white you see on the slide, if it were real blood, not dried up on a slide with mounting media, this would be where the plasma is. Again, there's nothing in it to resolve with a microscope. All these little kind of reddish, purplish spheres here, these are the red blood cells. They're usually described as little biconcave discs. Got about 8 micrometer diameter along the long way here, kind of like a donut that didn't make it. And these are some of the other formed elements. These are white blood cells, look like a couple of lymphocytes that produce antibodies for immunity. Now, just real quick, I'll show you my setup here. See, that's my little mini projector there, like a $3 monitor I got at one of the thrift stores. And there's my awesome computer there. That's my Raspberry Pi that projects them. It's kind of crazy, but that's what I'm working with. Okay, back in a bit.